Hello, my name is Benjamin Riley. This is a presentation on power distribution networks with mobile green ammonia fueled power generation. This talk was prepared for the 2022 AICHE annual meeting. I'll start off the talk with a motivating example. So at the University of Minnesota, we have collaborated with Runestone Electric Association. Runestone Electric Association is a rural electric cooperative or electric utility in western Minnesota, which you can see here. They shared with us that they experience temporary strains on their network frequently. So some examples are during the month of October, grain drying occurs, and so buses corresponding to farms have their loads substantially increased all at the same time when this energy-intensive agricultural activity occurs. Another example is during some weekends like Labor Day weekend, a lot of visitors from outside of the region will come and stay at remote cabins that normally have very low loads or power demands. But during those weekends, those demands will substantially increase. And Runestone even foresees a future where some of these visitors will bring their electric vehicles and want to charge them in these relatively remote locations. And so um, these demands strain their network, and in order to keep up with this demand, Runestone Electric Association would need to expand their distribution system capacity to these buses. But because they're relatively remote and also because these strains are temporary, these costly projects are relatively undesirable because these buses don't really need that extra load all that often. It's really only certain days throughout the year. And so what Runestone was after is a non-wires alternative for delivering that power. And the one that we chose to focus on is energy storage, and in particular, ammonia-based energy storage. So what we mean by ammonia-based energy storage is using ammonia-fed fuel cells or gensets, which are generators, for carbon-free power generation. We focus on ammonia because it can be produced from renewable resources, such as air, water, and then renewable power generation like solar or wind power. So we say it can be produced in a green manner. Additionally, we focus on ammonia as opposed to some other green chemicals like methanol or hydrogen because ammonia is particularly easy to store and transport. So when we think about the process of actually using ammonia for energy storage, we break it down into three main components. First, ammonia is synthesized and then stored for later use. Second, it's actually used to generate power. And then a power system is operated to deliver that power from where it's generated to where the end user and consumer is. Prior research on this topic has mainly focused on the first two steps, and it's neglected this third step of operating the power system to deliver the power. The way it's done this is by focusing on islanded power systems, or if it includes the power grid, it has massively simplified the treatment of that power grid so that there's not a detailed description of how it operates. Another alternative for how it's neglected this third step is by considering co-located synthesis of ammonia, consumption of ammonia, and then power demand in something like a microgrid so that there's no need to actually operate a power system to deliver that power. So the question that we want to focus on in this talk is how do we effectively incorporate ammonia-based energy storage into power systems to actually satisfy this third step that we see as being necessary for the eventual implementation of ammonia storage, or sorry, as ammonia as energy storage. So we'll focus on a system where we have an existing power distribution network where we have multiple operational scenarios, which are sets of time-varying loads. You can think of each operational scenario as something that represents a set of recurring operating conditions. For a tangible example, consider Runestone's case. One operational scenario could be a day in October for them. And so the recurring operating condition is that, each day in October, they have additional loads at agricultural buses corresponding to grain drying. And so one operational scenario, that operational scenario for October can be represented by like one representative day in October. So in this system, we have mobile ammonia gensets that can be relocated over time. We have ammonia storage capacity and mobile batteries that are available for investment, but are not currently a part of the existing distribution network. The goal of this talk is to develop a decision support tool for the distribution network operator to satisfy all of the demands in all of the operational scenarios at minimum total cost. When we think about the decision-making process for the system operator, we can break it into two different parts. First, investment decisions are made, which we'll denote as X. In these investment decisions, um, the choice to invest in particular ammonia gensets, particular batteries, and then where to locate ammonia storage and at what capacity, these decisions are made. Then after these decisions are made, the operational decisions are made for each operational scenario. And so in these scenario-specific operational decisions, things like power flows, device power injections, voltages, and so on are decision variables for the system operator. But also the location of the mobile batteries and the mobile gensets is a decision that they need to make. I'll highlight that while the investment decisions are only made once, the operational decisions are made independently for each operational scenario. We incorporate these decisions into an optimization model, where the goal is to minimize the sum of the weighted capital cost and the operating cost of the system, where the operating cost consists of conventional power generation cost, the cost of ammonia acquisition, whether it be synthesized by the system operator or purchased from a third party, and the cost of transporting the battery and the genset. And we minimize this combined cost subject to some constraints, and we break the constraints into 4 groups. The first group is constraints on the investment decisions that are feasible. The second group of constraints is on the power flow. And so these constraints are described as relaxed branch flow model, or the relaxed branch flow model in the literature. And they include reactive power flow and power losses. And so they are relatively accurate for the system that is being described. The third set of constraints is on the ammonia acquisition and storage. One example of a constraint in this set is that the amount of ammonia stored at a particular bus at the start of the time horizon must be equal to the amount that is stored at the end of the time horizon. We do this because the alternative is that the ammonia storage would be left at 0, or the ammonia storage would be empty at the end of the time horizon to avoid paying for more ammonia. But this would make operating the system quite difficult in subsequent time periods because the ammonia storage would always be empty between time horizons. So we avoid that using those constraints. The fourth set of constraints that we consider are on the operation of the gensets and the batteries. For instance, we enforce the fact that devices can only inject or withdraw power at buses if they are physically located at those buses, and that while devices are traveling or being relocated from one bus to another, they cannot operate at either bus while they are traveling. So we incorporate a travel time into the system for each pair of buses that the devices must, respect in their operation. This optimization model ends up being a convex mixed integer quadratically constrained program. We perform a case study on this system. We perform a case study using this optimization problem on a test system. The test system is shown on the right. It is from the literature. One feature I'll highlight about this test system is that there are two buses where conventional power generation are available. The first of which is the substation, bus 0, where uh, a potentially unlimited supply of power is available. And the second bus is bus 11, where there is actually less costly power that is available, but the power capacity or the potential amount of power that can be, withdrawn from this bus is limited. We consider a situation where there are 4 operational scenarios that describe the load profiles throughout this test system. Each operational scenario, it consists of 24-hour time periods, and 3 of the scenarios correspond to like qualitatively different strain scenarios, which represent days with recurring system stressors. So for Runestone's case, again, the recurring system stressor could be the increased loads due to grain drawing in October. And so there could be one strain scenario or one operational scenario that corresponds to one day in October with that recurring system stressor. We also include one nominal or normal scenario representing a typical day for the system. We consider 3 different sizes of gensets and 3 similar sizes of batteries, and we allow the system operator to purchase up to 2 of each size of each device. We solve this problem 3 different times. So the first time, we restrict the investment decisions so that only ammonia gensets can be purchased. Then we consider a situation where only batteries can be purchased. And finally, we consider a situation where you can purchase a combination of the two, which we will refer to as the full problem. We solve each of these 3 instances using the off-the-shelf solver Gurobi. The results of the case study will be presented using figures like the one you see on the left. So in this figure, there is a bar every hour. Each bar corresponds to a amount of power injection, where negative values correspond to batteries that are charging or withdrawing power from the system, and positive values correspond to actually injecting or producing power and putting it into the system. So that corresponds to a battery discharging or an ammonia genset producing power. Any place you see a stacked bar or like 2 bars on top of each other, that means there are 2 devices that are injecting or withdrawing power at the same time. Additionally, the bars are color-coded, where each color corresponds to a particular device location pair. So like we can see from this figure that battery 5 moves from bus 11 to bus 5 to bus 12, which you can see in this schematic. So here are the results for the battery-only problem. It ends up being optimal to invest in a 300 kilowatt and a 450 kilowatt battery, so 2 batteries. What we can see from these results is that batteries relocate relatively frequently to charge and discharge. So what we mean by that is oftentimes it is detrimental to charge in the same place that you need to discharge. And so if a battery runs out of stored power, rather than charging at the same place and adding even more load onto a already strained area in the network, the battery will move somewhere else so that it can recharge without adding additional strain to the system. But this, of course, leads to many relocations in the different scenarios. We also see that the batteries, when it's possible to do so, are located at bus 11 when they charge. The reason this is done is to save on conventional power cost. So the devices can withdraw power from the system at the location with the cheapest conventional power generation, as I highlighted previously, without incurring any additional losses from the power flowing over lines to get to the battery. In the generator only or the genset only problem, we see that the optimal investment is 2 300 kilowatt gensets. We can also see that in these 4 scenarios, the gensets very rarely need to relocate. The only time a genset relocates in any scenario is when genset 3 goes from bus 5 to bus 12 in scenario 1. We can also see that the ammonia gensets operate at many different locations in throughout these 4 scenarios. And the reason that's significant, so we can see that like at bus 5, 9, 12, 13, 14, at all of these locations, some amount of ammonia storage was built so that the gensets can operate there. And that's significant because there's a cost associated with building out that ammonia storage, and it could be possible that the gensets could be operated from just a few different buses that are used in all of the different scenarios, but we see that it ends up not being optimal, and that's a result of the fact that the ammonia storage capacity cost, so the cost of building an ammonia tank, is quite small, quite cheap when compared to the other costs that the system operator incurs. Finally, the optimal results of the full problem are to invest in a 450 kilowatt genset and a 200 kilowatt battery. We can see in these results that the battery and the genset end up playing different roles, if you will, in these 4 scenarios. So we see that the battery is seemingly used as much as possible, as much as it possibly can be used given its capacity. So for example, in scenario 1, it charges as much as it can, then discharges a full capacity's worth during this period of extended load. Then it recharges and relocates to be used at bus 12 for the last little bit of load. Similarly, in scenario 2, it charges at full capacity, discharges as much as possible or as quickly as possible, relocates, charges again, and then comes back and discharges before the end of the time horizon. Whereas the the genset serves a supporting role where it satisfies all of the load or all of the demand that the battery cannot satisfy while being used as much as possible. So in scenario 1, it covers this additional load that can't be covered by the battery in this middle period. And in scenario 2, it's used for any time period where the battery is either charging or relocating. This is particularly noteworthy because this flexible operation of the genset enables the 2 devices together to operate in ways that the multiple batteries could not operate on their own. So again, scenario 2 really highlights this behavior because in this case, the genset operates throughout this extended time period between hour 15 and hour 22, where if it were a battery, there would not be enough time for it to recharge by the end of the time horizon or in this period here. But because it's a genset that doesn't need to recharge, it can satisfy all of this additional demand that the battery can't quite cover without having any sort of operational restriction or constraint due to recharging and relocating. We can see here from the optimal cost breakdown per problem instance, where we have the battery only problem instance, genset only problem instance, and the genset and battery instance, that 1, the combined cost of energy, which is the cost of conventional power generation, plus the cost of ammonia that is used for power generation, we see that it is generally lower when batteries are used. So the sum of these 2 numbers is at its lowest when only batteries are used. And again, that is because the batteries get power from the distribution system, so from the sources of conventional power generation like bus 11, and then use that to satisfy the additional demand, whereas the gensets use ammonia, which is just generally more costly. But in exchange, the capital cost and the cost of transportation ends up being lower for gensets because the batteries that are needed to satisfy all of the demand, and they end up being a little bit oversized, if you will, or they're sized for the largest demand scenario that they see, the largest operational scenario that they see. That makes sense, largest in terms of energy. And again, they have to relocate more frequently to charge and discharge. And a key takeaway, of course, is that using both types of devices, both gensets and batteries, enables you to reduce the total cost of your system, um, as opposed to the optimal choice of only gensets or the optimal choice of only batteries, and that the capital cost of this situation remains relatively low, while the the combined cost of energy is not nearly as high as if you're only using ammonia. So the key findings or takeaways from these results, this case study, is that because ammonia gensets do not need to recharge, one, they do not need to relocate as often as batteries do, so you save on transportation cost. And two, they end up operating more flexibly, like in that one scenario I highlighted. They can perform roles that a battery actually could not because they would need to recharge in between periods of discharging. Ultimately, batteries seem to be preferred for short-term strains that are low in total amount of energy. This is because the cost per unit energy that's injected by the battery is lower than the cost of ammonia. Gensets are preferred for long-term high energy strains because the cost of storage capacity ends up being much cheaper for the batteries. What this means is the cost of a ammonia storage tank in terms of amount of energy is much less than additional storage capacity in a battery. And ultimately, the combination of both types of storage is optimal when multiple types of strains are considered. By multiple types of strains, we mean multiple operational scenarios with different types of strains. We'd like to acknowledge the state of Minnesota and their renewable development account for funding this effort. Thank you for listening. For more information, see the preprint that accompanies this presentation.